Your calculator, please.
I didn't realize that. What do you want?
Why does it no one else do that?
It's more like. It's like. It's not great. Like a. It's like during a pandemic, but it doesn't say you need.
Well, no, but I just like the program, like they don't have
Right, there's no rules that you can't.
But that's what I mean, like it's not.
But you can't have notes.
Right.
You can't have notes.
So it's gonna be kind of gray. It's like it's technically notes, but it's on your calculator. You're allowed to have.
Oh, also, so I also learned this. You go to app, you go down. It's like they keep it's like it's
It was not. Oh, like that.
What did you get on that?
Very excited.
Okay, this is the last set of notes for this unit.
Mine got 33.
Okay, we're going to talk about inverse trig functions. We have 6 of them, 6 inverse trig functions, but only 3 of them are going to produce unique derivative rules. But let me read the notes here. None of the 6 trig functions is one-to-one, meaning that if we were to look at them, they're all going to fail the vertical line test. So none of them are going to be functions unless we restrict their domain. So this is what an inverse sine will look like. It's basically a sine function that's flipped on the side, and you can see that, because of that, it's not going to pass vertical line test. So with all of the inverse trig functions, we're always going to have to restrict their domain. It's not really going to matter for us too much, but just it's good to know that on its own, these are not going to be functions. It's only a function if we can force it to live between 2 intervals. So arcsine and sine are inverse functions, which means that if we were to put one inside the other, they're going to cancel each other out. So if we remember e to the x and natural log of x, they have a way of canceling each other out. Same thing with if those arcsine and sine or sine and arcsine. Okay, so they're all so that when they cancel each other out, what that means by that is if I insert one into the other, everything will go away except x. Okay. Now there are multiple ways to represent inverse trig. Sometimes you may see it in terms of this notation, arcsine. Sometimes you may see inverse sine. This is not really raised to negative first power like how we would if it was like sine squared. If it was sine squared, then we would put it outside of bracket. It's actually being squared. That -1 is not raised to negative first power. It is just it's a notation for inverse sine. So if you see arcsine or that sine -1, they mean the same thing. Just have to recognize both notations. Okay. Sometimes on the AP exam you may see this notation. Sometimes you may see this notation, but they mean the same thing. Now, with these inverse trig derivatives or inverse trig functions, they also come with its own derivative rules. So with a graph like this, we can also create a slope formula that can tell us the steepness of any point on this curve. I know this feels intimidating, but we're going to practice later on looking for patterns and helping us remember, find a ways to memorize these rules. So arcsine's derivative is just u prime over square root of 1 minus u squared. Your u value is always what's inside that arcsine function. Arctangent's derivative is u prime over 1 plus u squared. This is the only one without any square roots. And then arcsecant's derivative is u prime over the absolute value of u times square root of u squared minus 1. Now these are the unique ones, because what do you notice about arc cosine, inverse cotangent, and inverse cosecant? They're just the negative versions of the ones on the left, right? So arc cosine is just a negative version of arc sine. Arc cotangent is a negative version. And these are convenient as well because these all have they all start with, they all are related to cosine, cotangent, and secant. And we know from before, the way we memorize our derivative rules, these all produce negative derivatives. So we're going to line them up the same way and memorize them accordingly. So we'll talk about how to memorize these rules, or ways to focus on memorizing those rules a little bit later. Let me just do some review before we move into our derivative. So let's look at example 1 here. Example 1 says, find tangent of arc cosine of root 2 over 2. So essentially, we're going to create a triangle with this behavior. Okay, so arc cosine root 2 over 2 is basically saying what theta value will allow cosine to be root 2 over 2. So in other words, what will cause cosine of theta to be root 2 over 2? Okay. And if we can create a triangle with that behavior, we can then ask the tangent of that triangle. Okay. So the first thing we do for this, we can create a triangle. Actually, we're going to use this triangle for this problem here. So theta has already been established. Root 2 over 2, that's just adjacent over hypotenuse. So root 2 over 2. And if we use Pythagorean theorem, we can find that third missing side, a squared plus b squared equals c squared. That's also going to end up being root 2. So now that inside the bracket is going to help fill out our triangle. And now we're just asking for what is tangent of theta. So all of this is one big representation of theta. So now what's tangent of theta going to be equal to? 1. Yeah, so equal to root 2 over root 2, which is equal to 1. So here are the steps. We're going to draw the triangle, label the angle theta, label the sides according to what's inside the bracket, and then use Pythagorean theorem to find all the missing sides, and then we can turn around and ask what is the tangent of the triangle that we see. All right, so let's try that process for example 2. Find cosine of arc sine of 5 over 13. So this is basically saying, let's create a triangle where sine of theta is equal to 5 over 13. So if we want to create a triangle where sine of theta equals 5 over 13, where can we put the 5 and the 13?
5
Opposite. And 13 is hypotenuse. Yep. Okay. Pythagorean theorem can help you get to that last missing side, a squared plus b squared equals c squared. You can use your calculator. It ends up giving us 12. And now that we have the triangle figured out, we can basically ask cosine of this whole big is this bracket is a big representation of theta here. So what's cosine of theta equal to? Cosine of theta, cosine of this triangle, cosine of theta equals 12. Yeah, 12. That's our answer. Okay, next page. And we're going to apply a similar process for example 3. It's just that now we're dealing with variables, but the process is similar. We're going to focus on building a triangle with this behavior. So we want to create a triangle where tangent of theta is equal to 3x. There is no denominator, so I'm going to put a 1 to represent what's in the denominator so we can see it more clearly. 3x, the same thing as 3x over 1. That way we can have a more clear representation of what we want inside our triangle. So now our triangle here, here's our theta. So where can we put the 3x and the 1? Opposite. And the 1 is adjacent. Okay. Pythagorean theorem to help us find that third side. A squared plus b squared equals c squared. So we know that c squared is equal to 1 squared plus 3x squared. That's end up being 1 plus 9x squared. If I want to solve for c, c is simply, or the hypotenuse is simply 1 plus 9x squared. So that's going to be my hypotenuse. And now we can simply ask, what is the secant of theta? We have everything that we need from inside the bracket to fill out our triangle. What's secant of theta going to be equal to? Good. Hypotenuse over adjacent, yes. Because secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so therefore secant is hypotenuse over adjacent. So we can say this is secant of arctangent 3x is equal to root 1 plus 9x squared all over 1, or you can drop the 1, and that's fine as well. There's a way to find the derivative using implicit method, but I'm just going to have us practice the derivative rules that we see above, and we're just going to practice getting used to them. So number 4, find the derivative of y equals arc sine of x. So x is our u value, and we're simply going to apply the rule u prime over square root of 1 minus u squared. Okay, so let's follow the rule. U prime, what's u prime going to be? 1, yep. Over the square root of 1 minus u squared. X squared, yeah, and that's it. So this is the slope formula for whatever this graph looks like. Okay. And we're not going to do the implicit, we're just going to practice the derivative rule here.
Did we get these formulas?
I'm sorry?
Did we get these formulas?
No, we have memorized them, yeah. Okay. So we'll practice, after we get through these problems, we'll practice working on memorizing those rules, yeah.
Are we going to use the implicit later, or are we just not doing
No, we're not doing it. Yeah. The implicit is a way to avoid these derivative rules, but it just takes longer and it's not efficient. And I prefer us to just practice with these derivative rules. So we're not going to do the implicit. Okay, y equals arctangent of 4x. So let's find the formula for arctangent, u prime over 1 plus u squared. Okay, so there's our formula. What's our u value? 4x. Okay, so let's just go through our derivative formula. U prime. What's u prime going to be? 4. Okay, 4 over 1 plus. Good. So we make sure that we square the entire u value. So it ends up being 16x squared. So again, this is the slope formula for whatever this graph looks like. All right, find y prime for 2 arc secant of 3x squared. What's our u value? 3 squared, okay. Let me write the formula here so I can. All right, so let's just follow what the formula says. Y prime equals. Numerator is u prime. What's u prime? Yep, 6x. Over the absolute value of u, absolute value of 3x squared. Square root of u squared minus 1. It's u squared. Yeah. If you don't clean up, it's fine. I'm just going to. If you want to cancel the x's, you can, and the 6 and 3, you can. The absolute value will have to stay though.
And the 2 just goes away because it's the derivative.
Oh, sorry, my bad. The 2 needs to stay. It's a coefficient, so I forgot to include that 2 there. So I just want to show you what the cleaned up version is, even though we don't have to do it. So 12 divided by 3 is 4. So the 12 and 3 can reduce. One of the x's can cancel out. So 4 over the absolute value of x. And we can't do anything inside the square root.
You said you don't have to.
Yeah, you don't have to simplify it. No. Okay, we'll skip 8, but let's look at 7 here. 7 says find y prime for y equals x arc cosine of 2x. We obviously need to rely on arc cosine of 2x as derivative, but is there anything else that we have to?
The x.
Which is requiring us to use what? Product rule. Yeah, so we need to recognize, okay, x and arc cosine of 2x, those are 2 separate functions. And because of that, we have to rely on product rule to get through this derivative. Okay, try this one. See if you can work your way through this one here. So I'm purposely changing the notation here just so we can get used to the fact that arc cosine and inverse cosine, they're the same. So you can write in either form. I just want us to recognize that these are the same and that they're interchangeable notations.
Why is it 1 minus 4x squared and not 1 minus 2x?
It is 1 minus 2x squared. It's just the 2x squared is parentheses squared. And I just skipped a step here and I made it 4x squared.
Don't do anything with the arc cosine 2x. Just
Yeah, you just leave it in that form, right? Mhm. All right, let's turn to page 24. We're just going to practice through our derivative rules. Okay, page 24. All right, see if we can try 39. The rules are above. We're just going to practice applying these rules, and then at the end, I will walk through a way to memorize these rules.
How did it become negative?
Oh, with the arc cosine? You mean here?
Cosine, just cosine.
Oh, right here?
Yeah.
I just want to show that these are interchangeable notations. So arc cosine is the same thing as inverse cosine. So I just want us to be comfortable with both notations. But if you want to write as arc cosine 2x, that's fine as well.
The 2x square on the end, if that.
Yeah, I just want to show that I skipped a step here. It's u squared, which is 2x quantity squared, which I can clean up to be 4x squared.
You like further simplify.
Yeah, but I wouldn't. Oh, yeah, I wouldn't go through the trouble. And also, want to make sure that we don't do this, that we don't cancel the square roots and the square out. That minus sign is preventing us. But if you want to fold this out, you can. But I wouldn't. I wouldn't take. Yeah, it would be. I don't think it's worth the hassle. Yeah. If you do it though, it's not wrong. For 44, I would rewrite the problem so you can get ready for the derivative. All right, so 44 here, x to the 1/2, that's my u value, the derivative of that, power rule, 1/2 x to the negative 1/2, all over 1 plus u squared. Root x squared is just x. I can clean this up to be 1 over 2 root x. 1 over 2 root x, I can have that 2 root x come down and share the same denominator space as this denominator. So 1 over 2 root x times 1 plus x. All right, what do you see with 46? We got to go through what? Product rule. All right, try that. Okay, f prime g plus f g prime, x squared becomes 2x. G and f stays the same. G prime, r tangent 5x is u prime over 1 plus u squared. 5 over 1 plus 25x squared. You don't have to clean up. I just made it so that the f and g prime and combine into one fraction. All right, 47. H of t equals sine of r cosine of t. There's a function within a function here, so we're going to go through what? Chain rule, yeah. So let's identify the outside and inside and take turns with each derivative. Does anybody still need to look at 46? Thanks. Okay. All right, so outside derivative, what does sine become? Cosine. So it's cosine of u. I mean, I guess it's chain rule, but it's also just the derivative for sine of u. You would have gone through chain rule anyway, cosine of u times u prime. So I guess we could have seen that without having to go through this whole extra notation. Okay, so now u prime, the derivative of arc cosine of t, similar to arc sine, just with a negative in front. Okay, we can actually clean this up. What do you think cosine of arc cosine of t is going to become? Just t, yeah. They're going to basically cancel each other out, so.
Or like when you're taking the outside, wouldn't sine be like cosine u times u prime?
Yeah, cosine. So basically it's this. I don't have to go through this since if we just relied on the derivative for sine of u, it has a built-in chain rule. So maybe that just feels confusing to go through this. Basically, this is good enough for us to walk through this process.
So we're not finding the inside derivative.
We did. The u prime is just that arc cosine of t, which is -1 over square root of 1 minus t squared. So sine of u is cosine of u times u prime. What's our u value? Arc cosine of t. And the derivative of that would just be this derivative rule that we just talked about. Yeah. So maybe this formula is better used if I have a more extended chain rule, but yeah, I guess this rule is good enough since our sine derivative already has a built-in chain rule in it. Okay. Next one here, natural log of u. What's the derivative there? What's our derivative rule there? Natural log of u becomes what? U prime over u. And then we can apply the arctangent rule for the second part. Okay, so natural log of t squared plus 4. T squared plus 4 is our u value, so u prime over u. So just 2t over t squared plus 4. Careful that you're not trying to cancel anything out. You cannot cancel across addition and subtraction. Next up, arctangent of t over 2. If you want to think of it as 1/2 t to help you with the u prime later, you can. The 1/2 is going to stay, that's the coefficient. And our derivative rule is u prime over 1 plus u squared. 1/2 and 1/2 becomes 1/4. I'm just going to put that 4 in the denominator to share with this space. And that made this 1 plus t squared over 4. Oh, 1/2 times 1/2 is 1/4. I just made that 1/4 with the 4 in the same. I just shifted it down to the same denominator space. Okay, let's go back to page 21. Let me talk about the derivative rules in terms of patterns to help us work towards memorizing them. Okay, again, I'm just going to focus on these three since these are really the unique ones. The other three are just negative versions of them. Okay, look at those three rules there. What's common between all three rules?
Oh, you prime.
Right, so that's nice, right? All the numerators are the same. You just have to worry about the denominator. The denominator is what's causing it to look complicated, right? So numerators all the same. Okay, good. What's similar with all the denominators?
U squared.
And
One.
1. So they all have 1 in u squared. There's just different combinations, right? So I like to start off with arctangent. That's the easiest one. It has no square root. It has no negative sign, no absolute value. It's simply just 1 plus u squared. If you do u squared plus 1, that's fine as well. The order doesn't matter, but we just know that it's u squared and 1 added together. Okay. From here, I like to go to the most complicated one. The most complicated one is the arcsecant. It's got the square root, it's got the minus sign, it's got the absolute value. So we know there's an absolute value of u here. There's a square root, and then there's some combination of u squared and 1. So the way I remember it is that sometimes we forget, wait, what comes first? Is it the 1 or the u squared? It's going to be the u squared minus 1. And what helps me remember that the u squared comes first is the fact that the u's are next to each other. So there's an absolute value of u. The u's are next to each other, so I know that u is going to come first, u squared minus 1. And what helps me with this is that if I see this pattern, then I can know that my arch sign will look a little different than this. Right? It's still a square root, but instead of u squared minus 1, this is going to be what? 1 minus u squared. So that's how I go about working through my derivative rules. I fill out all my numerators first, get the simplest one to show up, work on the most complicated one, because this helps me organize the order of my u squared and 1. And if I can see this pattern, I can make a slight adjustment for a change for arch sign. And then the arc cosine, arc cotangent, arc cosecant, we can line them up the same way that we do our derivative rules. And then for the ones, we can just copy the exact same one as the one next to them, and then just put a negative sign in front, and that will be the other three rules. All right, so I would like for us to practice these rules. So there are some related race problems that we're not going to do. So let's just use those empty spaces for practice. So if you can turn to page 17. We did 38, but we didn't do 39. So let's use page 17, 39 as practice for us writing out these. Okay, so this is page 17. Let's write down all the rules. In the order that we would do them in if it was a regular 6 trig functions. Okay, so I'm going to start off. I know they're all going to be involving numerator and denominator, so we know the numerator is easy. It's just u prime. I'm going to start off with arctangents. I know they all involve 1 and u squared, but arctangent is the cleanest looking one. It's just 1 plus u squared. Next up, arcsecant. It's got the absolute value. That makes it look messy. It's got the square roots. I know there's a u squared and 1 involved. They're going to be subtracted, but I'm going to say u squared minus 1. That helps because I know my u's are next to each other, so that helps me remember u squared is going to come first, followed by the minus 1. And if I can see this in front of me, then I can make a slight adjustment to make it a little different than arcsecant. So 1 minus u squared. Okay, if I have these 3 in front of me, then these 3 feels a lot easier for me to write out. I can just copy the ones across and just put a negative in front. Okay, if you're still feeling a little iffy about these rules, I mean, we still have another week. So if we do this every day, I think we'll get it eventually. Okay, so let's do it one more time. This time on page 18. Give it a try, see how we do. Page 18, copy down those rules and see where we are. And then we'll be done for the class. Speed is best though. Use your calculator.
No.
Okay, let's check how we did. Okay, so we'll begin our test review tomorrow. I'll give you a test review packet. We'll have 4 days to work through them. And then I'll also, I should be able to give back your quizzes tomorrow as well.
These, including this year.
What'd you get all of them?
I got.
No, I didn't. Let's go. Or take
The
it.
admissions guys said they don't even look at AP score stuff.
Oh.
Yeah.
Yeah, I have.
Like, it's just if you want, if you get credit when you come to school, or not, like, it doesn't help you get into schools.
Fucking free it, not take them.
But like, it saves you a lot of money, obviously, to do well.
Oh, Jack, you can.
What?
It's that every day. My biggest brother, they come for it, it's like.
What do you think about your? You have like a high GPA.
School.
That's what it
Yeah,
is.
they call it that, and so we do that since then.
What's your GP?